Yes, it is common for solid-state control boards to have dry contacts that only close when the control voltage is applied to one side of the contact. This behavior stems from the fact that solid-state control boards rely on electronic components for switching, rather than employing a traditional mechanical coil. In essence, the application of the control voltage triggers the electronic components to establish a conductive pathway between the two contacts. This pathway facilitates the flow of current, resulting in the closure of the contacts and enabling current to traverse the circuit. Conversely, when the control voltage is removed, the electronic components cease to maintain the conductive pathway, causing the contacts to open. This particular configuration is often categorized as a make-before-break contact. The designation signifies that contacts close before the existing circuit is interrupted. This characteristic is crucial in scenarios where the contacts govern a load that cannot tolerate any disruption, however momentary. Solid-state control boards are prevalent in heating systems due to their enhanced efficiency and reliability compared to mechanical controls. Furthermore, their compact design allows seamless integration into electronic systems. To further elaborate on the functionality of these solid-state relays, consider the fundamental principles governing their operation. Unlike traditional electromechanical relays that depend on the magnetic force generated by a coil to physically move contacts, solid-state relays utilize semiconductor devices, such as transistors, silicon-controlled rectifiers, or triacs, to switch electrical circuits. These semiconductor devices act as electronic switches, turning on or off in response to an applied control voltage or current. The absence of moving parts in solid-state relays contributes to their increased lifespan, reduced maintenance requirements, and immunity to mechanical wear and tear. The dry contact terminology refers to a type of switch or relay contact that does not supply any voltage or current to the circuit it is controlling. Instead, it merely provides an electrical connection, either open or closed depending on its state. In the context of solid-state relays, dry contacts are often implemented using semiconductor switches that are electrically isolated from the control circuitry. This isolation ensures that the control signal does not directly influence the load circuit, providing a clean and reliable switching operation. When the control voltage is applied to the solid-state control board, it activates the appropriate semiconductor switch, causing the dry contact to close. This closure completes the circuit, allowing current to flow through the load. When the control voltage is removed, the semiconductor switch turns off, opening the dry contact and interrupting the current flow. The make-before-break characteristic is a specific type of contact behavior where the new connection is established before the existing connection is broken. This ensures a continuous flow of current, preventing any momentary interruptions that could disrupt the operation of sensitive equipment. In solid-state relays with make-before-break contacts, the semiconductor switch is designed to close the new contact before opening the old one. This is typically achieved by using a combination of transistors or other semiconductor devices that are carefully timed to ensure a smooth transition. The use of solid-state control boards in heating systems offers several advantages over traditional mechanical controls. Firstly, solid-state relays are more energy efficient than electromechanical relays, as they consume less power to operate. This can lead to significant energy savings over time, especially in large heating systems with numerous control points. Secondly, solid-state relays are more reliable than mechanical relays, as they have no moving parts to wear out or fail. This reduces the need for maintenance and repairs, resulting in lower operating costs. Thirdly, solid-state control boards are more compact than mechanical controls, allowing for greater flexibility in system design and installation. This is particularly important in modern heating systems, where space is often limited. In addition to these advantages, solid-state control boards also offer improved control accuracy and responsiveness. The use of electronic components allows for precise control of the heating system, ensuring optimal performance and energy efficiency. Solid-state relays can also switch much faster than mechanical relays, enabling quicker response times to changes in demand. To ensure the safe and reliable operation of solid-state control boards, it is essential to follow proper installation and wiring procedures. Firstly, always consult the manufacturer's instructions and specifications before installing or wiring any solid-state control board. These instructions will provide detailed information on the proper wiring connections, voltage requirements, and safety precautions. Secondly, use appropriately sized wiring and connectors to ensure that the circuit can handle the current load. Overloading the wiring can cause overheating and potentially lead to a fire hazard. Thirdly, protect the solid-state control board from moisture, dust, and other environmental contaminants. These contaminants can damage the electronic components and cause the board to malfunction. Fourthly, provide adequate ventilation to prevent the solid-state control board from overheating. Overheating can reduce the lifespan of the electronic components and potentially lead to failure. Fifthly, use a surge protector to protect the solid-state control board from voltage spikes and surges. These surges can damage the electronic components and cause the board to malfunction. Finally, regularly inspect the solid-state control board for any signs of damage or wear. If any damage is detected, replace the board immediately to prevent further problems. It is also important to understand the different types of solid-state relays available and their specific applications. Firstly, alternating current solid-state relays are designed for switching alternating current loads, such as motors, heaters, and lighting systems. These relays typically use triacs as the switching element and are available in a wide range of voltage and current ratings. Secondly, direct current solid-state relays are designed for switching direct current loads such as solenoids, valves, and power supplies. These relays typically use transistors or field effect transistors as the switching element and are also available in a wide range of voltage and current ratings. Thirdly, hybrid solid-state relays combine the advantages of both alternating current and direct current solid-state relays. These relays typically use a combination of triacs and transistors to switch both alternating current and direct current loads. In addition to these basic types, there are also specialized solid-state relays designed for specific applications such as phase control, zero-crossing switching, and proportional control. Phase control solid-state relays allow for precise control of the alternating current voltage applied to the load, enabling dimming of lights or speed control of motors. Zero-crossing switching solid-state relays switch the load only when the alternating current voltage crosses zero, minimizing the electromagnetic interference. Proportional control solid-state relays allow for proportional control of the load based on an analog input signal, enabling precise temperature or pressure control. When selecting a solid-state relay for a specific application, it is important to consider several factors, including the voltage and current rating, the type of load, the switching speed, and the operating temperature. The voltage and current rating must be sufficient to handle the load without overheating or damaging the relay. The type of load will determine the type of solid-state relay required, alternating current, direct current, or hybrid. The switching speed will determine how quickly the relay can respond to changes in demand. The operating temperature must be within the specified range for the relay to function reliably. In addition to these factors, it is also important to consider the safety features of the solid-state relay. Some solid-state relays include built-in overcurrent protection, overvoltage protection, and short-circuit protection. These features can help to prevent damage to the relay and the load in the event of a fault. The National Electrical Code, or NEC, provides guidelines for the safe installation and wiring of electrical equipment, including solid-state control boards and relays. It is important to follow these guidelines to ensure the safety of personnel and equipment. Article 725, one of the NEC covers remote control, signaling, and power-limited circuits, which often include circuits used for controlling solid-state relays. Article 300.11 of the NEC addresses securing and supporting wiring. Wiring must be properly supported to prevent strain on connections. Article 310.15 of the NEC covers ampacity of conductors. Conductors must be sized appropriately for the load they will carry to prevent overheating. Article 430 of the NEC covers motors, motor circuits, and controllers. Solid-state motor starters and controllers must comply with these requirements. Section 110.3 of the NEC covers examination, identification, installation, and use of equipment. Equipment must be installed and used in accordance with its listing and labeling. It is important to note that the NEC is updated regularly, so it is essential to consult the latest edition to ensure compliance. Additionally, local codes and regulations may also apply, so it is important to check with the local authorities to determine the specific requirements for your area. In conclusion, solid-state control boards with dry contacts that require control voltage for closure are a common and efficient solution in modern heating systems. Their reliability, compact design, and precise control capabilities make them a valuable component for ensuring optimal performance and energy efficiency. By understanding the principles of operation, proper installation procedures, and relevant safety codes, one can effectively utilize solid-state control boards to create safe and reliable heating systems.